Yeah, hello everybody, and thanks for coming. So I would like to start by acknowledging the Turrbal, Jagera, and Yugara people as the traditional owners of the land which we are meeting on here today, and pay my respect to their elders past and present. So in today's talk, as Ian already said, I will try to give you an overview on the groundwater recharge and hydrogeological connectivity processes in the Great Artesian Basin and that one.
Yeah.
Okay.
Yeah.
All right, and in adjacent basins. So there will not just be hydrogeology, there will also be some geology, so don't be scared. I would like to start with acknowledgements, just really to emphasize that this work has been done very collaboratively during the last approximately 10 years, in particular with Geoscience Australia. So we've had many projects together with Geoscience Australia, like the bioregional assessment, geological bioregional assessment also, and also Geoscience Australia's recent project assessing the status of groundwater in the Great Artesian Basin. Also Queensland Office of Groundwater Impact Assessment, University of Queensland, including Harald Hoffman, who has joined CSIRO recently, and ANSTO. So some of the work that I'm presenting today has been funded by GSAQ, which is the Gas Industry, Social and Environmental Research Alliance, and by AIG-GSAQ, which is the Australian Coal Association Research Program. And also I would like to acknowledge support from industry, Queensland Department of Regional Development, Manufacturing and Water, Water New South Wales, and DPIE Water, who have helped us a lot with the research during the last 10 years. So in today's presentation is roughly separated into 3 parts. So first, I'd like to give you an overview on the geology and hydrogeology of the Great Artesian Basin and adjacent sedimentary basins. And then I'd like to focus a bit on groundwater recharge estimation and assessment of flow patterns in the GAB. And then finally also look a bit closer into the assessment of connectivity in the Great Artesian Basin with under or overlying formations or basins. So I start with the overview on the geology and hydrogeology of the Great Artesian Basin. So this is just taken from a joint capability statement that we have done with Geoscience Australia recently. And I think it just shows some of the facts about the GAB quite nicely. So firstly, its size. So this is a Great Artesian Basin. It is one of the largest aquifer systems in the world. It covers about 1.7 million square kilometers, and about 65% of that area is in Queensland. But it also shows that there are quite a lot of water users or competing interests in the Great Artesian Basin. So the water from the GAB is used for town water supplies, for example, here in Longreach in the past, and other towns as well. It is also, of course, has some petroleum and also coal seam gas, and of course also agriculture as well, and some other uses. And more recently also is investigated for carbon capture and storage. So as I already said, the GAB is one of the largest aquifer systems in the world. It covers approximately 22% of the Australian continent. As you can see here on this image, the GAB is very deep. So in some of the GAB, it's up to about 2.5 kilometers, 3 kilometers deep. It also includes multiple sub-basins, such as the Surat Basin, which is here in the east, the Eromanga Basin, which is the largest part of the GAB, and the Carpentaria Basin in the northern part of the GAB. And here in the very eastern part, there's also the Clarence-Morton Basin. So it is underlined by several older basins, such as the Canada Basin here in New South Wales, the Galilee Basin here, the Kube Basin, and the Bowen Basin. There are a large number of mapped geological structures throughout the GAB, so I just projected them as vertical structures on that surface, but of course they're not all vertical. And also there are probably much more structures that are not mapped. The GAB also supports very significant indigenous cultural values and groundwater-dependent ecosystems. So they're shown here on this map as these yellow dots. So as you can probably also see, many of the GDEs appear to be associated with geological structures, which is probably not too surprising for many geologists, but the pathways and the source aquifer of the different springs is not always well understood. But generally, in order to really understand how this GDEs function, it is important to understand recharge and connectivity as well. So within the GAB, it's not just one aquifer, right? So it's several aquifers, and the major ones of those are the Katna-Oe-Hooray formation, which is a composite of different aquifers that are, for simplicity, put together, and also the Hutton sandstone and the precipice sandstone. So the precipice sandstone is the deepest one. The recharge beds are mostly located along the eastern margin of the GAB. So, for example, here for the Katna-Oe-Hooray formation, and also here in the southwestern margin as well. One thing that is also quite important, and I will come back to that, is that there are many Cenozoic volcanic aquifer systems located along the eastern margin of the GAB. I'm not sure how well you can see them here, but you all know the main range volcanics, which are here just west of Brisbane, and in New South Wales, the Nandewar volcanics and the Warrumbungle volcanics as well. So the flow path in the GAB, generally the groundwater mostly flows from Queensland into New South Wales and also into South Australia. But there are some local variations, and if you think back of the image that I showed you with the structures, there's also likely to be a fair bit of compartmentalization induced by those structures as well. And some of it I will come back to later. So this kind of is a simple representation of the GAB. So as I said, it's not just one aquifer or one aquitard, it's a sequence of several aquifers and several aquitards. And at the edge of it, we quite typically have this Cenozoic volcanics. So on the right-hand side, you see an example of Cenozoic volcanics, which is Thorn rocks from Mount Kaputta National Park in New South Wales. So that's one of the nicest examples that I've seen in Australia. And from the recharge point of view and hydrogeology point of view, this is just a piece of it that has fallen down, but you can see this columnar jointing. And I think you can quite well imagine with all these joints that water probably infiltrates and recharges quite fast through these kind of rocks. Then on the other hand, we have one of the best aquifers here, which is the precipice sandstone. So it's probably not very clear, but it's composed mostly of quartz sand with only very minor cementation. So again, if you think about how groundwater moves through these rocks, I think you can imagine that it moves quite fast through those kind of rocks. On the other hand, we have aquitards or low permeability units, such as this claystone or mudstone, and at the other end of the spectrum. So if water, you can imagine probably quite easily that water will not flow through that very fast. So I'm now just coming to the groundwater recharge estimation. So one of the methods that we mostly use in Austria is the chloride mass balance. And we just use that because it's quite simple, it's cheap, we have a lot of data for it, and we can apply it in many different areas. So the assumption behind the chloride mass balance is that chloride in groundwater is sourced from rainfall and not from rock weathering or from interactions with streams or deeper aquifers. Another assumption is that chloride is conservative in the system, so that there are no sources or sinks. Another assumption is that chloride flux does not change over time and that there's no recycling of chloride in the system. So if these conditions can be met, then we can estimate recharge from the chloride deposition and from the concentration of chloride in groundwater. So this is the workflow. So I will not go through that now in detail. So if you're interested, you can just drop me an email or look at that report. It's described there in a lot of detail, but we first estimate recharge at a point scale, and then we upscale it using regression equations and kriging with rainfall, soils, vegetation, and other parameters as covariates. So rainfall, annual rainfall throughout the GAB is quite variable, as you can imagine. So we have very high rates of rainfall in the north, so more than 1,000 millimeters per year. We also have relatively high rainfall here along the eastern margin, in particular in those elevated areas like the main range or the Warrumbungles in New South Wales. And then as you move further west, of course, the rainfall is very low, so maybe 200 millimeters per year, so much lower. So we have also estimated the chloride deposition throughout the GAB, and that's very high in the north and in the east, but otherwise pretty small. And again, if you were interested in those data sets, they're all available from our data repository. So we have then estimated the median recharge in the GAB and in adjacent basins. So if you look at the values up here, I forgot my glasses, so I cannot read anything, but up here it's high, very high. And in the eastern part, it's also quite high. So in particular in those areas that I mentioned earlier, like the main range or here the Warren-Bunker volcanics and so on in these Cenozoic volcanic systems. So they probably function as recharge, as preferential recharge areas at the edge of the GAB, although we don't really know exactly how much of that percolates down into the GAB. So on the other hand, the recharge rates are very small in the western part of the GAB, so less than 1 millimeter a year. So if you think rainfall, there might be 200 millimeters a year or so. So then clearly less than 1% of the rainfall is actually recharging the aquifers there. So very little. So that's just the volcanic systems. There are a lot of limitations and uncertainties associated with the chloride mass balance. And we have about 22,000 samples in groundwater samples in the GAB in the different databases, but only about 4,000 of them have chloride concentration records that meet our selection criteria, for example, with regards to depth. For this method, we only use shallow groundwater samples. There are also a lot of spatial data gaps in areas close to the recharge basin, the Northern Seward Basin, for example. So one of the questions is, this is shallow recharge that we estimated with that, but we also want to know how much of the shallow recharge ends up in the deeper basins. So we went out to collect samples from the GAB, and again, so this is this simple conceptual model of how water moves through the aquifers, and we collected samples from a lot of environmental tracers for this purpose. So we have kind of our initial idea before we go out sampling. So at the spot 1 here, near the recharge areas, we expect that the water rapidly infiltrates into some of the formations and that it is very young. So young groundwater we can identify with traces such as tritium, which is naturally in the atmosphere and also partly still in the atmosphere from atmospheric bomb tests that have been conducted several decades ago. So with that, we can identify groundwater samples that are up to about 50, 60 years old. So as we move along the flow path from 1 to 2 to 3 and so on, this changes. So at 2 already and then 3, we don't expect there to be any tritium in the groundwater already. So it has all decayed to below the detection limit. And then on the other hand, we'll use other traces such as carbon-14, which has a half-life of about 5,000 years. So it can help us to identify waters of up to about 40 or 50,000 years. And then as we move to 4 and 5, we also have other traces such as chlorine-36, which has a half-life of 300,000 years and which can allow us to identify and estimate very old groundwater ages. So as we are here at 5, we already have groundwaters in the GAB that are several 100,000 years or maybe even 1 million years old. So the water moves through the system very slowly, but it's also very long distances as well, of course. So I just see whether that will work. I think that's a video. So that's just an example of a bore that we have sampled in the GAB. And the temperature of that was 82 degrees. So in order to collect samples for environmental tracer, we want to get an airtight sample, so an airtight connection. And you can imagine that didn't work here, right? So it was very high pressure and very high temperature. And the bore is about, I think, about 1.5 kilometers deep. So this is it's probably one of the more difficult bores to sample in the GAB, and we didn't get close to it. But with a surface water pool, we managed to collect the sample safely. So there are a lot of challenges associated with collecting groundwater samples in the GAB. So I just quickly want to show you how we estimated deep recharge to the precipice and hardened sandstone in the Northern Seward Basin. So the Northern Seward Basin is this area here in the southeast, and then in the northern part of the Seward Basin. So the yellow dots are the available chlorine-36 values for the hardened sandstone, and the blue values are the available chlorine-36 values for the precipice sandstone. So this is the area that we're focusing on. So here that just shows you the concentrations or the values of chlorine-36. Here the largest dots correspond to high values of chlorine-36, and modern groundwaters or very young groundwaters. On the other hand, the small dots correspond to groundwaters where the chlorine-36 has already decayed due to radioactive decay, and these are very old, right? So I mentioned earlier the half-life of chlorine-36 is about 300,000 years, so there's not much of it left here, and they will be already potentially hundreds of thousands of years old. So here in the Hutton sandstone, this is for the Hutton sandstone, which is the second deepest aquifer in the GAB. In this area, we have a surface water catchment where the flow is mostly towards the north rather than to the south, which is quite counterintuitive. So we expect intuitively that the water flows from the outer part of the basin towards the deeper part of the basin, but that's not the case here. And that probably indicates some structural control, and if you look here at the surface water divide, that also coincides with some map faults. So carbon-14 is mostly below detection limit for most samples, which is not shown here. But carbon-14, as I said earlier, can help us to identify waters up to about 50,000 years old. So most of the water samples are older than that. You can also see that chlorine-36 extends beyond the outcrop of the Hutton sandstone. And one thing to point out is also that there are numerous springs within the outcrop. So from the groundwater age tracer, we estimated flow velocities of about 1 meter a year. So that's how fast water flows through the system in some areas, but it's highly variable, of course. We have used the tracers to estimate deep recharge at 452 megaliters per year, and that compares to a median of 32 gigaliters a year, which we have estimated from the chloride mass balance that I have showed you earlier. And the reason for that is probably that a lot of the water that recharges in the outcrop areas almost immediately discharges or with very short flow paths to the springs that are located in this area. And furthermore, probably another reason is that the Hutton sandstone is not a clean sandstone like the precipice sandstone, but it's a dual porosity system where flow happens only in a small part of the aquifer. So for the precipice sandstone, it looks completely different. So again, the big dots are young groundwaters and the small dots are old groundwaters. So you can see that chlorine-36 remains significantly higher in the precipice sandstone than within the overlying Hutton sandstone. So that's a bit counterintuitive too, because we usually assume that the deeper formation contains older water, but that's not the case here. And that relates back to the picture of the precipice sandstone, the core that I showed you earlier, which is mostly just quartz with very little cementation. So we use the tracers here to estimate deep recharge at 1.1 to 6.6 gigaliters per year. And that compares pretty well with the chloride mass balance. So the other technique that I showed earlier, where the median was 17 gigaliters a year. So there are also some springs within the discharge, within the outcrop beds here with higher discharge rates. But the difference between the different estimation techniques is much lower than for the Hutton sandstone. So again, nevertheless, there is some rejected recharge, and that's an example of one of the springs here on the right-hand side, or a spring-fed creek. So there's many of those kind of creeks in the outcrop areas of the precipice sandstone and the Hutton sandstone as well. So each of the techniques has some uncertainties and limitations, and estimates recharge at very different temporal and spatial scales. So now if we look at the whole GAB, again, this is the values of chlorine-36. So again, same thing. Big dots are young groundwaters, small dots are old groundwaters. So we have combined historic and new data, and have it using all those data, we have identified faster and slower flow paths. For example, there's a fast flow path in the southern Coonamble embayment, which is this little sub-basin of the Sword Basin, and also here in central Queensland as well. On the other hand, we have very rapid decrease of chlorine-36 and carbon-14 as well in some other areas. Like in this area, for example, within 10 kilometers or 15 kilometers of the outcrop beds for the formation, we already have virtually no carbon-14 and no chlorine-36 in the water anymore, or it's close to the natural background. So this rapid decrease of chlorine-36 and carbon-14 from the recharge beds to the deeper basin occurs in several areas, and there are several potential explanations for that. So we used other traces such as krypton-81, which is less influenced by geochemical processes than chlorine-36, to test that, to see whether it shows the same patterns, and it does show the same patterns as chlorine-36 as well. So that probably indicates, or it could indicate, for example, that there's stagnant flow conditions, that there's upwards discharge of older, deeper groundwater, or that there's aquifer compartmentalization. And like I said earlier, there's a lot of faulting in the GEB happening, so that's definitely possible as well. So this is an example of one of the faster flow paths. So this is in the southern Coonamble embayment, which is the southern part of the Surat Basin in New South Wales. And here you can see what I showed on the map. So these bigger dots here, they extend much further away from the edge of the basin. So we have young groundwaters much further away from the edge of the basin than what we have along this, what we called slow flow paths. And the horizontal flow velocity that we have estimated along this southern flow path was between 0.2 to 1.5 meters a year. So now lastly, I'd like to talk about connectivity within the GEB and adjacent basins a little bit. So there are several potential connectivity pathways that we have. This is probably not all, there could be others as well. So number one is, for example, faults with significant vertical displacements. Number two is stratigraphic contacts at the basin margin or adjacent to basement heights. Number three are igneous intrusions, such as dikes here. And for the dikes, probably the dike itself is not a pathway, but a fracturing associated with the dike. So when the dike intrudes into a sedimentary rock, it does disturb it significantly. And number four is sills. Of course, the sills are also associated with a dike somewhere. And then number five are fracture zones. So in order to understand what pathways may be present and whether they are actual pathways or just potential pathways, we integrate multiple lines of evidence to develop conceptual hydrogeological models of recharge processes and potential connectivity pathways. So in this case, we want to understand connectivity between the Kannada Basin, the Surat Basin, and volcanics. So we use, of course, hydrogeology, we use geology, geomorphology, geophysics, such as seismic or AAM, and we use hydraulics, environmental chemistry, hydrochemistry, and then in many cases, we also develop groundwater models to test different conceptual models. So one of the goals is, of course, to identify potential pathways, and the other goal is if we have identified some pathways or potential pathways, are there actual pathways? Is there really some connectivity for fluid flow or water? So for fluid flow, like water or gas, and in this case, we did that in the Narrabri area. So here, the Narrabri area is shown on this image, on both images. So this was in relation to the Narrabri gas project area. So the Narrabri gas project area is outlined here on the right image by this white line, and on the left image by this black line. So we have done some TEM here. So we have done several lines across this area. And then we have also looked at existing seismic images. So as you can see here, this Narrabri gas project area is quite closely located to this former volcanic center, so Cenozoic volcanics. So the extent of those volcanics was much larger in the past than what it is now. So there are dikes associated, of course, with this volcanic center. So we looked at some of the seismic sections, and this is an example that's outside the Narrabri gas project area. But you can see that there are some dikes within this area that really also show up in seismic images. So recently, we have done, about 5 months ago, we have done an airborne electromagnetic survey. So seismic images that targeted petroleum reservoirs usually don't really target so much the upper couple of 100 meters. So they usually focus on the deeper part of the subsurface, maybe 700-800 meters and below. On the other hand, the airborne electromagnetic survey here focus on the upper 400 or 500 meters. So it's quite complementary. So in this case, we have contracted SkyTem, which is one of the companies that does airborne electromagnetic surveys in Australia, to do that survey for us. And they have flown about about 80 lines for us. So on the right-hand side, we can see the different lines that they have done with the helicopter. So they carry this equipment with receiver and transmitter underneath the helicopter and then fly across all these lines. So this is an example of what we got out of that. So that's we've only done that about 4 or 5 months ago, so that's still preliminary. But on the bottom, that gives you an example of the kind of image that we get for each of the lines. So this particular image, which is in the southern part of this area, the Narrabri gas project area, you can see that there's a very sharp contrast between the base of the Pilliga sandstone, which is this blue unit, and which is the major aquifer in this area, and the underlying strata. So that there's such a sharp contrast, we think probably indicates that there's no significant connectivity because the hydraulic properties in the underlying formations are very different from the Pilliga sandstone, and the water in the underlying formations is much more saline than the Pilliga sandstone. So if there was any significant discharge along this line, then that probably would show up in this image. So based on the seismic data, the AEM data, which are not included in here yet, the geological data, we come up with these conceptual models of potential connectivity pathways. So here we have the Surat Basin, which is everything above this black dashed line. And underneath that, we have the Kannada Basin. So we have identified different potential hydrogeological pathways. So for example, igneous intrusions like dikes, number one here. We have also identified some sills. We have thinning adjacent to the basement heights of some of the formations. We have stratigraphic contacts near the basin margin of the Kannada Basin here. We have some fault zones with vertical, significant vertical displacements. But for these fault zones, we do not see them extending from the Kannada Basin into the Surat Basin. So they seem to be more or less restricted to the Kannada Basin. We also have fracture zones. And we also have, of course, groundwater recharge to the Pilliga sandstone through the outcropping basalt. But now, again, as I said earlier, the question is, even if there are potential connectivity pathways, so what, right? Is there actually connectivity or not? So that's the question that's really hard to answer for us. And that's where we look at multiple lines of evidence. So earlier, when I showed the map of the chlorine-36 for the whole GAP, I showed that the areas where we have a rapid decrease of chlorine-36 from the recharge beds to the Debo Basin. So this is one of the areas here. So we have these big dots on the right-hand side of the image in the GAP aquifers, the Pilliga sandstone, which is this kind of beige color. And then it rapidly decreases here already from very high values within a few kilometers to very low values. And one of the possible explanations is that there's some very old groundwater coming up from the Kannada Basin. So it would only require a little, very tiny bit into the Pilliga sandstone. But there are also other explanations, as always, in geology and hydrogeology. So we also use other parameters as well, additional lines of evidence. And one of the easiest method to use is just basic hydrochemistry. So in this case, the Pilliga sandstone recharge waters here in the east are very fresh. So the electrical conductivity is below 200 microsiemens per centimeter, which is extremely fresh for groundwater. The pH is very low, so about 5 to 6, which is almost the same as rainwater. And there's no very low concentrations of methane and very high carbon-14 and chlorine-36. And then in the Pilliga sandstone, we see a bit of a change from here to here, from the eastern part of the Narrabri gas project area, which is shown by this purple line, to the western part of the Narrabri gas project area. So the EC increases to about 100,000 microsiemens. There's a higher pH, some methane, and also low carbon-14 and chlorine-36. On the other hand, the underlying waters in the Kannada Basin have electrical conductivity, so salinity is between 5,000 to 20,000 microsiemens. They have high pH and high methane. So if there's any significant water coming up from the Kannada Basin into the Pilliga sandstone, because of the contrast in this hydrochemical signatures, we would expect that to see from the hydrochemistry. So if you look spatially at it, so we have here the Narrabri gas project area by this outlined by this red area. we have very low salinity in the south and southeast, so it's less than about 200 microsiemens per centimeter. So again, that's extremely fresh for groundwater. That's some of the freshest groundwater probably in the GAP. So that means because the water in the underlying Canada Basin, which hosts the coal seams here, is very saline, this means that there's not really any evidence that there's any water from the Canada Basin coming up into the Pilliga sandstone here. But we do see that we have a little bit of an increase of salinity towards the north and northwest, starting approximately here in the center. So that could indicate that there's a little bit of interaction with the underlying or overlying formation possible in the northwest of the Narrabri gas project area, because the Pilliga sandstone itself is quite a clean and quartzose sandstone, very similar to the precipice sandstone, the image that I showed you earlier. And the same is shown by methane. So if there was any upwards discharge from the Pilliga from the Canada Basin, the coal seams to the Pilliga sandstone, then we would expect there to be any methane as well. But there is no methane in the southern and southeastern part of the Pilliga sandstone as well, or very low concentrations. But there's a little bit of an increase towards the northwest, which could indicate that there's a bit of connectivity there towards the northwest. So this is, I think, the second last slide that I will show you, but it's also an interesting connectivity indicator. So mantle helium, we have started using that more recently, and here on the right-hand side, you see the samples that we have in the Great Artesian Basin. So big dots here correspond to a high percentage of mantle helium. Small dots correspond to a low or no low percentage or no mantle helium. So elevated helium-3, helium-4 ratios refer to primordial or mantle helium. So that's helium that's existing since the formation of planet Earth. And that indicates that there's a possible deep mantle helium component. So that means the water has to come from very deep. So this could be related to Cenozoic igneous intrusions at the edge of the GAP. So for example, here in the Conumbal embayment, but it could also be related elsewhere to deep-seated basement faults. For example, in the Eromanga Basin here. So as I said earlier on the conceptual model, we don't really see any deep-seated faults extending from the Canada Basin into the Great Artesian Basin here. But if you look at the same thing in the Eromanga Basin, which is this area here, we see that towards the western part of the area where the Eromanga Basin is underlined by the Manaru platform, which is shown in this section here, we have very significant vertical displacements of about 500 meters. So the aquifers are completely displaced by 500 meters. And in many cases, aquifers are interfacing or juxtaposed against aquithards. So it's definitely possible here that we have mantle helium coming up from the deeper part of the subsurface into shallow aquifers. So the conclusions, we think that recharge and connectivity processes I think that recharge and connectivity processes within the GAP are spatially highly variable. And one thing I think that we learned is that the geological and hydrogeological understanding from one area cannot necessarily be easily extrapolated to other parts of the GAP without conducting regional geological and hydrogeological assessments. So I think the best way to understand that is, as in probably most geoscientific cases, using multiple lines of geoscientific evidence together to build a better understanding. So for us, the next steps here are, I think we have characterized recharge pretty well in the GAP, although there are still some knowledge gaps and some data gaps. But I think the next thing that we would like to focus is more on discharge, in particular on the Great Artesian Basin springs, to understand their source aquifer and also their climate resilience. And there's a big data gap in Northern Australia. So in the Carpentaria Basin, we have virtually no environmental trace or data. So that's those kind of things that we want to do next. Thank you.